A pale shark glides through dim water, its flattened snout projecting far beyond a loosely hanging mouth. Then the jaws shoot forward, open around prey, and retract before the animal's body reaches the target. If you watched only the final instant, the mouth might seem launched by a hidden mechanical spring. The movement belongs to Mitsukurina austoni, the goblin shark, and it is a genuine feeding adaptation. Its jaws do not detach, break, or act independently from muscles and connective tissues. They travel along an extreme path because the shark's anatomy stores mobility where most faces appear fixed. The central question is why a slow-looking deep-water predator evolved such extraordinary reach. Answering it requires following a target from detection beneath the snout to capture between slender teeth. Each stage connects sensory information, jaw suspension, muscle action, fluid movement, and prey escape. High-speed recordings have exposed the sequence, while rare encounters still limit knowledge of natural hunting. Its long rostrum seems to separate the mouth from prey, yet the projecting jaws erase that distance. The shark approaches quietly, detects nearby movement or electrical signals, and commits to one sudden expansion. That commitment is costly if mistimed, making close-range information essential before the strike begins. Our investigation enters the mouth at rest and follows every moving element through capture and recovery. Goblin sharks occur in deep waters across widely separated ocean regions, often along continental and island slopes. Most records come from fisheries rather than planned observations of undisturbed animals. Their soft bodies, reduced-looking musculature, and relatively small fins suggest a lifestyle unlike sustained high-speed pursuit. Such appearance supports an interpretation of limited cruising performance, but direct field measurements remain scarce. The elongated rostrum carries numerous pores connected to electroreceptive organs called ampullae of Lorenzini. These receptors detect weak electric fields produced by living tissue in seawater. They likely help locate prey at close range where light is faint and visual information is unreliable. The small eyes may still contribute, and no evidence justifies calling the shark blind. When you imagine its approach, picture multiple senses narrowing uncertainty, rather than one supernatural detector finding everything. The rostrum passes over a potential target before the underslung mouth reaches the same position. That geometry makes forward jaw projection especially useful, turning sensory contact near the snout into immediate capture range. Teeth are long and narrow near the front, suited to grasping rather than crushing hard material. Stomach records indicate a varied diet including fishes and invertebrates. Although samples are limited, different prey may demand different strike angles, and captive recordings cannot reproduce every deep water encounter. Unlike human jaws, shark upper jaws are not fused directly to the skull. Cartilage, ligaments, and muscle arrangements permit both upper and lower jaw elements to move. In goblin sharks, that mobility is amplified into exceptional forward protrusion. At rest, the jaws sit retracted beneath the head, supported by stretched connective structures. The mouth begins opening as the upper jaw moves forward and the lower jaw rotates downward. Expansion of the oral cavity pulls water inward, helping carry the target toward the teeth. The jaws then close, near maximum reach, before returning toward their resting position. This cycle combines ram from the body with suction and projection from the head. High-speed video separates the strike into coordinated phases too rapid for ordinary footage to resolve clearly. The head first elevates slightly as the mouth opens, and the jaws begin their forward travel. Protrusion accelerates as ligaments release. Stored elastic energy and muscles guide the cartilages. The upper and lower jaws move together like an extending frame rather than a simple hinged door. Their forward displacement increases the volume behind the mouth, generating inflow around nearby prey. Closing secures the target while retraction draws the captured item back beneath the skull. Elastic recoil is a mainstream mechanical explanation, supported by the speed and anatomical arrangement. Muscle action remains necessary for positioning, loading, control, and recovery, so the jaw is not a passive catapult. Researchers sometimes describe the system as slingshot feeding because stored strain contributes to rapid projection. The label is useful only when it points toward measurable mechanics instead of suggesting an actual separate sling. Dissections reveal ligaments and jaw connections, but dead tissue cannot reproduce living tension perfectly. Computed imaging can map cartilage geometry, though models depend on assumptions about material stiffness. High-speed captive footage directly records movement, yet stressed or recently captured animals may behave differently from wild sharks. These limitations make the motion certain while leaving its exact natural frequency unknown. Not every approach probably ends with maximal projection, because smaller adjustments may handle weak or poorly positioned targets. Available recordings show substantial variation among strikes, rather than one rigid program. Distance, prey motion, body angle, and sensory confidence could change when the jaws begin closing. Its narrow teeth pierce soft targets and reduce the force needed for initial penetration. Those teeth may be vulnerable to twisting loads, favoring rapid retraction after the bite. A detected signal triggers orientation. The body closes distance. Projection overtakes the target, and retraction restores control. If the target escapes sideways before commitment, aborting may conserve energy and avoid damaging the jaw apparatus. Such aborted sequences are poorly documented, leaving important decisions invisible between successful strikes. Suction contributes another uncertainty because water flow around a moving shark is difficult to measure directly. The expanding mouth should create inward flow, but its strength in open, deep water requires better testing. Computer models can generate predictions, not direct observations, and must be checked against living motion. The strongest conclusion is therefore mechanical. Projection rapidly extends capture range and accompanies oral expansion. For life in dim water, that range changes the economics of hunting. A predator need not overtake agile prey across long distances if it can close the final gap explosively. When you combine quiet approach with a sudden jaw extension, slow cruising no longer means uniformly slow feeding. Energy can be conserved during searching, then released during the fraction of an encounter that determines success. Electroreception guides attention. Subdued swimming limits warning. Jaw projection closes distance. And slender teeth hold soft prey. This sequence suits a habitat where encounters may be uncommon and missed opportunities expensive. The rostrum's sensory surface gains space for receptors, while pushing the resting mouth farther behind the leading edge. Projection compensates for that separation, allowing sensory specialization and capture geometry to coexist. Natural selection did not design both features in advance, but compatible variations could accumulate across generations. Relatives and fossil forms help place the anatomy historically, although behavior cannot be observed in fossils. The modern goblin shark belongs to an ancient lineage, yet its living body is not an unchanged prehistoric machine. Cartilage, ligaments, senses, and metabolism continue responding to present ecological pressures. Calling the strike primitive would miss how specialized its coordination has become. Calling it perfect would also be misleading, because every extension trades reach against stability and structural risk. Fisheries bring most specimens to science, creating both information and conservation concern. Deep water sharks often grow slowly and may reproduce at rates that limit recovery from sustained capture. Specific population trends for goblin sharks remain difficult to estimate because records are sparse and uneven. Bycatch location can map occurrence, but absence from catches does not prove absence from an area. Better ecological knowledge matters because a spectacular feeding mechanism cannot protect a population from repeated mortality. It also matters for robotics, where elastic energy storage can inspire rapid motion, though biology offers principles rather than blueprints. Future evidence must capture undisturbed strikes in the habitat where prey, pressure, and darkness shape performance. Low-light cameras could reveal approach speed, failed attempts, and whether the rostrum contacts targets before projection. Synchronized views could reconstruct jaw paths without relying on a single deceptive angle. Slow measurements around controlled strikes could test how much suction assists the moving teeth. Detailed imaging of fresh tissue could improve estimates of ligament strain and cartilage motion. Repeated observations across body sizes might show whether juveniles and adults use the mechanism differently. Diet evidence matched to jaw damage could reveal which prey impose the greatest mechanical costs. Population monitoring could connect feeding ecology with vulnerability to deep water fisheries. If you return to the pale silhouette, the long snout now marks the beginning of a sensory corridor. Beneath it, retracted jaws wait within tissues capable of storing movement and releasing it forward. The strike is neither a cinematic trick nor proof of aggression toward anything nearby. It is a close-range solution for converting uncertain detection into a brief capture opportunity. Many details of target choice remain unknown because natural attacks have rarely been recorded. The anatomy proves capacity. High-speed footage proves coordinated projection, and ecological interpretation explains why reach could matter. Future field sequences may revise the balance among approach, suction, elastic recoil, and tooth contact. Until then, every model should remain anchored to visible movement rather than imagined encounters. One electrical trace may guide the head, one extension may bridge the gap, and one missed strike may cost a rare meal. The goblin shark's slingshot jaw is an extreme mobile feeding system whose natural use still awaits sustained deep-sea observation.